Hi everyone, today I would like to talk about norm, correlation, inequalities, and much more. So this is the fourth video in the video series that I'm creating about the numerical linear algebra and optimization. So if you have not already watched the first three videos, I will put a link in the description. Please go ahead and watch those. So let's start talking about the norm. Now, Euclidean norm is the most widely used norm, or also is known as L2 norm. This is the symbol for L2 norm. Now, it's defined as follows. So Euclidean norm is defined as a square root of each component square when you add them up then together, right? So these two are both equivalent definition. So this is when you define vector x like this, as we explained, we define it usually as a column vector. So x transpose x, this is another definition, very nice definition. So your x transpose is gonna be a row vector, x1, x2, all the way to xn, and then x is a column vector. When you multiply them, then this component is multiplied by this one is multiplied by this, xn multiplied by xn, and then you add them all. So you get xi square, sigma xi square. Okay, good. Now, but we have other type of norm as well, like x1 norm or L1 norm. L1 norm is has a lot of application in compressed sensing and also has a L1 regularization in machine learning in neural network. So it's defined as a sum of absolute value of the each component, right? So this is the vector x that we define. Absolute value of x1 plus absolute value of x2 all the way to absolute value of xn is equal to L1 norm. We have also L infinity norm, which is equal to maximum value of this absolute value of each component. So absolute value of x1, absolute value of x2, absolute value of xn, which one is the maximum value? Which one is the largest one, right? So for example, let's define something. I would say x sample here, let's say x is 1, 2, 3, right? The L2 norm is a square root of 1 square plus 2 square plus 3 square, right? Is a square root of 14. The L1 norm is equal to 1 plus 2 plus 3. So all the components are positive, no need to put the absolute value, of course, you get 6. Then the L infinity norm, right, is equal to, what is the maximum value of 1, 2, 3, which is equal to 3? Good. Let's talk about the properties of norm. So norm is non-negative. It's one of the properties actually. This one, norm is always non-negative. The smallest you can get is equal to 0, right? Why is that? So norm is defined like this: x1 x squared plus x2 squared all the way to xn squared, right? So we are adding a bunch of positive numbers because each xi squared is positive, right? So definitely is non-negative. Now is equal to 0 if and only if all the values are 0. So it's equal to 0 if x1 equal to x2 all the way to equal to xn. Okay, good. These two properties that I have, probably 3 and 4. Now, since norm is always non-negative, when you multiply x, vector x, by a scalar, well, this scalar beta can be positive or negative, or b can be positive or negative. It can be negative 2, it can be 3, it can be negative 10. Doesn't really matter. When you take a norm of this vector, we know norm is positive. So when you actually extract this vector, this constant b, you have to use an absolute value because the resulting scalar resulting number resulting number should be positive quantity. Okay, good. This property is usually known as non-negative homogeneity. Okay. Now, triangular inequality, very famous inequality, well-known inequality, right? It's that norm satisfies the triangular inequality as well. It says the norm of x plus y is smaller than norm of x plus norm of y. We will see numerous definitions of triangular inequality in this video, right? When norm satisfies, just remember norm satisfies the, at least L2 norm satisfies the triangular inequality. But these properties that I have are in general for all the norms. Okay, good. Now I want to talk about another concept which is called root mean square, RMS. RMS also is used widely in circuit and machine learning as RMSE. Time series prediction, time series forecasting. This is like one of the measures for the like quality of the model that you design as RMSE, root mean square error, and it has numerous applications. It's defined as follows. This x is a vector. RMS of vector x, again, the vector x is defined x1, x2, all the way to xn. The root mean square of vector x is defined as a square root of x1 square, x2 square, plus xn square divided by n. What is n? N is the length of vector. But wait, what is this square root of x1 square plus x2 square all the way to xn square? It's nothing but a norm, L2 norm. Right? I'm gonna put this L2 norm. So RMS of x, root mean square of x, is defined as L2 norm of the vector divided by a square root of the length. What's the application of this RMS? You see, when you have a vector that has a length of 10, right? It wouldn't really be fair if we compare this vector to a vector that has a length of 1000. So RMS is usually used to compare the normal vectors with different length. It's kind of like a standardized norm of vector to a square root of the length, right? So keep that into consideration. Okay. Now, I'm posing a question here. How do you find the norm in general? Well, norm of the f of x. This can be anything, right? Or norm of f of x and y. So we just saw that the definition of L2 norm x is equal to a square root of x transpose x, right? Now, for example, you want to find the norm of x plus y, right? It's used a lot, norm of x plus y, sum of the two vector, right? Each one is a vector. So x is this, x1, x2, all the way to xn. Y is this, y1, y2, all the way to yn, right? So norm of x plus y is equal to a square root of, what do we do here? This is equal to a square root of norm of x plus y square. But this one is equal to this, x plus y transpose times x plus y. Remember, I defined the definition of one of the definition of the norm was this. This is very important. I said this is very important quantity. So this is equal to x plus y transpose times x plus y. We just expand this. How do we do that? X transpose times x. This is norm of x. X transpose times y plus y transpose times x. This is this times y transpose plus times y transpose times y. Okay. Now, in the second video I explained about that when you have x transpose times y, you get this, right? Which is equal to this, which is equal to y transpose x. So x transpose y and y transpose x are the same. That's why we have two x transpose y. Okay, so that's just one example how to manipulate the norm of sum of two vectors. Great. Let's talk about one of the well-known inequalities in optimization and also in the context of random processes in general. It's called Chebyshev inequality. Currently, we are considering for vectors actually. So what does Chebyshev inequality say? It says that if you have n-dimensional vector, again, it's good to have the x here. We find x to be this n-dimensional vector. If k of the values have this property, if k values have the property that the absolute value of the components is greater than the number a, what do I mean? Right? What do I mean by that? Let's say that x1, x2, all the way to xk, right? Their absolute value is greater than a. Let's say, for example, a here is 5, x1 is 6, x2 is -10, their absolute value, right? x3 is 9, x all the way xk is, for example, 7, right? if each of these is greater than the absolute value is greater than A, then we have the following expression. Write the L2 norm square. So L2 norm itself is this. So now L2 norm square, it becomes x1 square plus x2 square all the way to xn square, right? But now wait, the first k term, let's say the first, any k, but since it's symmetric, I'm gonna choose the first k for simplicity. The first k, they have an their absolute value is greater than number a. So let's choose this one as the first k. So each of them is at least, each of these terms is at least a square, right? At least. So we have at least ka square, at least, right? We have at least ka square, at least. Now, the rest of the terms, they're all positive, right? Xk plus 1 square, xk plus 2 square, they're all square, they're at least positive. At lowest, they're 0, but at least they're not negative, right? So the norm of x, the Euclidean norm of x square is greater than or equal to ka square, which equality happens if the other terms are 0. And the first k actually term are equal to a, right? So this one is greater than that. Now, if you divide by a square, you get this quantity here. I wanted equation 1. Let's see, I have not used equation 1 anywhere. Yes, I'm going to use equation 1. So it says the norm of x, Euclidean norm of x square divided by a square is greater than or equal to k, right? Okay. So now remember that I defined the RMS, root mean square, as a norm of x divided by a square root of n. Now we can relate these two concepts together. We can write the Chebyshev inequality in terms of RMS. So I'm going to go ahead, write the norm of x to be root n times the RMS of x, right? Now let's plug it. Let's use this one as equation 2. Let's plug equation 2 in 1. What do I get? I get root n RMS of x square, which I get n times RMS of x square divided by a square is greater than or equal to k, right? So after I manipulate that, dividing by n both sides, then I get RMS of x square divided by a square is greater than or equal to k over n. Okay, this is a very interesting property relating the Chebyshev inequality. Writing Chebyshev inequality based on RMS, relating the number of elements that are at least greater than a, their absolute value greater than a, meaning that k, and the total number of elements, which is n, to the RMS and a. Okay. So this one will put some sort of an upper bound or lower bound on the how many elements on the RMS actually value, right? So usually what will happen is that you are told that how many values have an absolute value greater than, let's say, 5 or 6, so 10 of them, and then you can get some idea about the RMS and in a sense in terms of a norm, right? Okay, good. And remember k is smaller or equal to n, right? Okay. Now let's talk about triangular inequality, right? So we talk about triangular inequality in the context of a norm, but now in general, we talk about the triangular inequality in the context of distance between two vectors. So distance between vector A and B is defined as norm of A minus B. This is where the triangular inequality is getting its name, actually. So we are saying that assume that we have a triangle with the sides A, B, C, A, B, C. Okay, good. Right. So then define distance between A and B to be norm of A minus B. Right. Norm of A minus B. I'm gonna write it like this. right? Distance between A and B is equal to norm of A minus B. We defined that above. Distance between B and C is equal to norm of B minus C, and distance between A and C is equal to norm of A minus C. Now, go ahead and apply triangular inequality here. We get norm of A minus B, which is the distance, one of the sides. This side, let's say, and plus this side, B minus C, right? When you add them all together, it's gonna be greater than the length of the third side. That's what the triangular inequality says. And this is what this expression says. Plus norm of B minus C, the second side, is gonna be greater than equal to the third one, right? Now, let's see how we can actually see this one using the triangular inequality for the norm, right? Let me write A minus C, this one, in terms of A minus B plus B minus C, right? So when you add them up, the B's cancel out, negative B and B, right? So you get again A minus C. Let's apply the triangular inequality we had as one of the properties of a norm here, right? So take this one X, take this one Y, right? So X, norm of X plus Y is smaller or equal to norm of X plus norm of Y, right? So you can see that you can prove the triangularity for a distance. That's where the actual triangular inequality gets its name, related to the triangle and size of triangle. Okay, good. Now let's talk about the standard deviation. I had a video in the third video. I walk you through how to define a standard deviation in terms of random variables, and also how you define a standard deviation in terms of vector, right? I'm going to redefine these quantities, but if you have not watched the last video, the third video, I will put a link in the description. So variance of an n-dimensional vector x. So I defined that usually for a standard deviation, we start from the variance. So variance of an n-dimensional vector x is defined like that. These are all the definition, right? So here we are considering the vector, right? I talked about that, about the definition of a PMF and everything, that for a vector, we consider that all the elements are equal likely, right? So all of them have a PMF of 1 over n, right? So otherwise, the expectation in general, the expectation of x is defined as xi, p of xi, right? But this one is 1 over n, and therefore you get 1 over n times sigma I to n xi minus mu square. So in a sense, we are treating vector as like a random variable, but all with an equal probability, okay? And then what is this one? Now that we know a lot about the norm and the Euclidean norm, what is this? Right? Remember, sigma I to n of xi square was norm of x square, right? Now this one is sigma I to n xi minus mu square is equal to norm of x minus mu square, right? Where mu is sometimes defined as average of x, and the one we explained last video about the role of the one. It's just a one vector to make sure that since x is a vector, right? Mu is a number. We want to subtract. We cannot subtract the number from a vector, so we're gonna convert that number to a vector as well. Okay, good. This is variance. Now a standard deviation is nothing. A standard deviation is nothing but a square root of a variance. So we're gonna go ahead and take a square root of this quantity, this term here, to get this one. Let's see what equation, what are we doing in terms of equation? So this one deserves to be number 4 perhaps, and this one number 5. So take a square root of number 4, 1 over n become 1 over the square root of n, and the 2 we can remove, get rid of the 2, and we get x minus average of x times 1, right? So I have a note here for you to better understand this. X is a vector. What do I mean by average of x times 1? X is x1, x2, all the way to xn. Average of x is just a number, but 1, recall, 1 was this, 1, 1, all the way to 1. So we remember multiplication of a constant by a vector. You multiply that constant by every single component of that vector. So you get average of x for the whole vector, and then when you subtract them, you get a vector that each component is xi minus average of x. Okay, so this. Now, I also expand the definition of a norm here. That what I mean by norm, x minus average of x times 1 is equal to, remember, norm of x was equal to what? Xi square, right? So x1 minus average of x square plus x2 minus average of x square all the way plus xn minus average of x square, right? Okay, that's just expansion of the norm. Now I define the standard deviation as a measure of variability and dispersion from the mean. So if the standard deviation is equal to 0, this means that all the values are the same, right? Or all the values in a sense are equal to the mean. For example, let's say that you have some data, 1, 1, let's not use 1 here. Let's use 5, 5, 10. No, I want to use all the same for now. 5 and 5. What's the mean here? Without any calculation, the mean is equal to 5. But there is no variability in this data. All of them are the same. So in a sense, the standard deviation is equal to 0, right? Therefore, all the values are equal to the mean. The smaller the standard deviation, this means that the closer are the data points together. Okay, good. Now, another definition I have here for the mean, the fancy definition for the mean or average, and a standard deviation usually you see in the textbook, is the average of x is defined as well. Let's see, let's write it together. x1 plus x2 all the way to xn, right? Good. But we saw that in the second video, one of the application of this dot product is that you can get the sum of the elements of a vector using dot product. Remember, we had the A transpose X, or we had a 1 transpose X. We said that this gives you x1 plus x2 all the way to xn. I want to get the same thing as well. So I calculate 1 transpose x to get the sum of the element of x, and I divide it by n. This is a fancy definition for a mu. Okay, and the same thing, we can define the same thing for a standard deviation, x minus mu1, or another definition I have here for a standard deviation. There you go. I'm gonna copy this one and bring it there. And you see that this is also fancy definition for a standard deviation. Right. This is nothing but x remains as it is. This mu, I replace it by the definition that I have here. Let's make sure that I am naming them correctly. We have 5, and I'm going to use this one 6, and then use this one 7. You see in the equation 6, I'm going to just replace the mu for equation 7, right? And then the rest of them remain the same. This is another definition of the standard deviation based on some manipulation based on vector operation. Okay, good. Now, here I want to drive an expression based on a standard deviation, RMS, and average. So for that one, first I want to title this one expression or relationship between STD, average, and RMS. I would say method 1. This is one way to do that. Method 1. Write the standard deviation score. What's the definition of standard deviation? It was 1 over square root of n times norm of x minus average of x times 1. But write the standard deviation of x score. This is nothing but the variance. This is the variance of x. Okay. Let's see what do we do here. Now, use the definition of a norm we have. Norm of x, recall, norm of x square was x transpose times x. That's all I'm doing here. X minus average of x times 1 transpose times x minus average of x, right? Good. Let's expand this. Let's just calculate the, manipulate this expression. We get x transpose times x from here. We get x transpose times average of x times 1. Okay. Then we have average of x times 1 transpose, which is row vector. All the elements is average of x times x, and then average of x times 1 transpose times average of x times 1. Let's see. We get x transpose x. This is norm of x square. We have seen this many times. This is x transpose average of x, 1 transpose x. Remember, 1 is a vector, so 1 transpose makes sense. And this quantity. Now, before that, let's explain about some terms. X transpose x is norm of x square. We know that. Now, let's take a look at this. This x transpose is gonna be a row vector. x1, x2, all the way to xn. And this one is gonna be average of x. Right? So the result is gonna be a scalar. The same thing for this. So in a sense, these two are the same. How can you say that? See, x transpose times 1 vector is the same as 1 transpose times x. We have seen this. A transpose times b is equal to b transpose times a. And then average of x is just a scalar. Doesn't really matter. So these two terms are the same. That's why I have -2 here. But now, what is 1 transpose 1? 1 transpose 1 is this, and this is this. Is equal to 1 times 1 plus 1 times 1 plus 1, all the way 1 times 1. Is equal to n. Right? Good. And that's why I have this n here. Great. Now let's divide them by n that I have in here, this n. I get norm of x squared divided by n. What is this norm of x squared divided by n? Without any without going any further, what is this one? This is RMS, right? This is RMS square. This is RMS of x square. Minus 2 average square of x, right? Correct. Why is that? Why is minus this? We had 1 average here, right? It's good for people to become really familiar with these terms. 1 transpose x. I explained this numerous times. What is 1 transpose x? What is 1 transpose x? It's a sum of element of x, right? Sum of the element of x is 1 transpose x. Is x1 plus x2 all the way to xn. But wait, there is 1 over n here. So we get this. So we get average of x. When you multiply average of x by another average of x, you get average of x square. Okay, good. And then guess what? You have 1n here, you have 1n here. You divide them, you get 1 here. So you just have average of x square. Average of x square minus 2 average of x square gives you negative average of x square. Great. So finally, you will have this minus average of x square. But this one is just RMS square. Right? So you prove that a standard deviation square, or the variance, is equal to RMS square minus average of x square. Okay? Great. That's one way to prove it. That's one valid, very valid way to prove this. Another way is to look at it in terms of a random variable. What is a standard deviation square? Variance. What was the definition of the variance in the third video I defined? Very famous equation. Is the expected value of x square minus expected value of x square. But what is this? This is just average square. So already we get this one. Now, what is this expected value of x square? This expected value of x square We said that in the context of vector, we write the PMS, but we assume all of them have a PMF of 1 over n. It's sigma I to n xi squared times 1 over n. Okay? Now, what is this? This is just norm of x squared, right? So this one, in a sense, is norm of x squared over n. Well, this is just nothing but RMS of x, right? And that's what I wrote for you here. So in a sense, we get RMS of x squared minus average of x squared. This one, much faster. But we get the same result. Both of them are valid. Okay, so two ways to prove this expression. Variance of x is equal to RMS of x squared minus average of x squared. Good. So now I want to talk about the Chebyshev inequality for a standard deviation. It's the same concept, very much similar. But that one we just talked about the Chebyshev inequality for a component of x. Now I want to talk about that Chebyshev inequality for the standard deviation. Okay. You see, in the Chebyshev inequality, we said that assume each xi is greater than or equal to a. Now I want to say that the mean there, or xi minus average of x, right? So let's define the vector x to be like this, x1, x2, all the way to xn. So I want to say each component minus the average. So xi minus average of x is like, for example, x1 minus average of x. K of this component is greater than or equal to a in their absolute value. Okay, good. Like always, remember over there, what was the function we consider? We consider function norm of x squared. Oh, here we do the same thing. As a matter of fact, consider this. Consider this one to be y, right? It's going to be the same as Chebyshev inequality if you take this one to be y. Absolute value of y for k terms is greater than or equal to a, right? So we're going to construct the norm of y. What was norm of y? If you take this one, what was norm of y is y1 squared plus y2 squared all the way to yn squared, right? Now k of this term, let's take the first k. Doesn't matter, it's symmetric, doesn't matter. We are squaring all the terms and we are adding them. Let's take the first k term to be at least a. So we get ka squared, right? And then the other terms are non-negative. At worst case scenario, it can be 0, but they are non-negative. So this result is going to be greater than k over k squared. Okay, the same thing is here. So just replace y by the equivalent of x minus average of x times y. So this one is this. We consider this norm. We write it based on equivalent. Now we are all expert in this, based on the component-wise definition of the norm. And this is greater than the ka squared, right? Nothing new. Okay, now let's continue. Now remember that we defined the standard deviation of x squared, or the variance of x, to be like this. That was the definition we had in the third video. We just derived it in this video as well. Now this term has a meaning here. Is equal to n times variance, or n times the standard deviation of x squared, right? Why is that? You see this one, just multiply n by this. Multiply both sides by n, right? So that you get this. So in a sense, what you're going to get is that n times a standard deviation of x squared, or n times variance of x, is greater than or equal to ka squared. And then after manipulation, you get this one. So 7, equation 7, we get this one as equation 8. You see, over there, you had this one for RMS. Now you have this one for a standard deviation of x, right? So you get Chebyshev inequality for the standard deviation. The concept is very similar. If you let that xi minus average of x to be yi, then you get exactly a similar thing, right? So here we just subtract the average of x from each component of x. But the procedure is the same, right? And the reasoning is exactly what I actually said. Okay. Now that we know what is RMS, what is the Chebyshev inequality, what is the standard deviation, what is the variance, let's take a look at some of the properties of a standard deviation. Okay, adding a constant to a vector does not change the variance or a standard deviation. But why? First, what will happen when you add a constant to a vector in terms of the mean or the average value of that? So there are, as I said, multiple ways to look at that. If you look at that in terms of random variable case, I'm going to write it here. So if you have a random variable x with a mean of mu, now expected value of x plus c, where c is a constant, is going to be mu plus c, right? Okay, expectation is a linear operator, right? Now, in terms of a vector, it's the same thing. If the average of x is defined as x1 plus x2 all the way to xn divided by n, if you add c to every single component, what will happen is that you get x1 plus c, x2 plus c, all the way to xn plus c divided by n. But guess what? You get x1 plus x2 all the way to xn divided by n plus nc divided by n, which is c. So you get average of x plus c. So adding a constant to the vector will add the same constant to the mean of that vector. So that's easy. Well, now let's see what will happen to the standard deviation or variance. So I said assume the standard deviation of the x is denoted by the symbol sigma x, right? Now we want to find the standard deviation of x plus c. One way we're going to start now, we're familiar with the concept of standard deviation. We use directly the definition of standard deviation for a vector. So 1 over n, remember, norm of x plus c times 1. Remember, c is a constant, x is a vector. You can't just really add them all together, right? So here, for example, this c either should be like this, c times 1, or you can just define a vector c as all the elements to be c, right? But let's follow this one, c times 1. This is not c1, this is c times 1, vector 1. We all know what's the function of this one, minus average of x plus c1 times the vector 1, right? Because we are going to be able to subtract this one from the x plus c times 1, right? Otherwise, this average gives you a number. Great. Now, we just see that this quantity here, I just also prove it here as I wrote it as a note, is going to be average of x plus c, right? Good. Let's go. Let's continue. A standard deviation of x plus c is equal to 1 over a square root of n. X plus c, I just copy this one, minus, right? So let's take a look at this one. This expression requires some explanation here. Average of x plus c, I'm talking about this one. This is a constant, right? It's just a constant. When you multiply by 1, you get such a vector. You get average of x plus c and all the way to average of x plus c. Well, you can write them as a sum of two vectors, right? This one, you can write it like this, average of x, average of x, average of x, plus c, 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 right? And that's what I'm talking about here right now. Average of x times vector 1 minus c times vector 1. Why do I write it like that? Because I'm writing it like this because I want to subtract, I want to cancel this. That's the whole point, right? So what I'm going to have x minus average of x times 1 divided by a square root of n. Well, guess what? This is exactly a standard deviation of x. This is a definition of a standard deviation of x. Okay, so adding a constant to a vector will add the same constant to the mean. Therefore, it does not change the standard deviation or variance. Okay, good. I said here, or starting from the variance. I just manipulate the definition of the variance. Let's see what I have done here. Starting from variance, I'm considering a case of a random variable here. Expected value of x minus mu, but we know that now we want to calculate the x plus c. We know that the mu is going to be mu x plus c as well. The same constant is added to the mu. The c's cancel out, so we got x minus mu x, which is the same as, so one more step. This is going to be x minus mu x, which is going to be variance of x, right? Okay, good. Now, what if multiply a vector by c? Multiply the variance by c square and multiply the standard deviation by absolute value of c. What would happen to the mean? Before that, what would happen to the mean if I have a vector x, right? If I multiply by c, what's going to be the mean? The average of x, average of cx. Let's just do it here. Save some space. Average of cx is equal to what? Is equal to cc, not c1. cx1, cx2, all the way to cxn divided by n. What is going to be what? C average of x. So multiplying and function multiply a vector by c will multiply the mean of the vector by c as well. Okay, good. Now we want to calculate the standard deviation. We can start again from the definition. Let y to be cx. So this is a standard deviation of x. This is just a definition. We have seen it numerous times. Let y to be cx. We write the definition of a standard deviation of the y. The same thing as what we had above. Now we write it for y. We say a standard deviation of the cx now. We replace the y by cx. We have this. We realize that average of cx is equal to c times average of x. We saw this one times 1. Again, we know the role of 1. It's just to make sure that dimensionality match. Now we use the properties of norm. You see here, perhaps it would be useful if I write one more step. I can write c times average of x, this, right? You remember the first properties of norm, non-negative homogeneity, right? Non-negative homogeneity, isn't this the same thing? So you extract c is a constant with absolute value, and then you will get this stuff here. And then you copy and carry 1 over the square root of n as well. But guess what is this? This is just a standard deviation of x. This is this one, and then times absolute value c. So multiply a constant, multiply a vector by a constant, will multiply the absolute value of that constant by a standard deviation. Intuitively, it should be positive quantity, and that's why we have the absolute value. But that constant necessarily is not positive. And in a sense, squaring this will give you the variance. So multiplying a vector by constant will multiply the variance of that vector by the constant square. Okay. Perhaps we can make this one number 9, and we can make this one number 2. Okay. Good. Let's talk about the standardization. As a technique that is widely used in a context of machine learning and statistics, right? It's used to reduce the range of the features, right? Or normalize or standardize actually the features to zero mean and unit variance, right? Or unit standard deviation. Now, it's not the only technique. Normalization also is used. Various normalization, they change the features to -1 and 1, but this standardization is one of the most widely used, right? In the statistics, sometimes it's called a Z-score because of this Z. So it's defined also by Z. So what would happen? You're gonna go and subtract the vector x from the average. Each component of x is subtracted from average. So like this. You get something like that, x minus average of x xu minus average of x, like this, xn minus average of x, right? And you divide this by a standard deviation. Well, why does it give you the zero mean? If you take an average of this quantity, what would you get? Well, a standard deviation of x is just a number, right? So I want to show you something interesting here. Let's go ahead and apply average. Approaching this using random variable is very easy, but let's stick to this average definition. Average z 1 over std of x, because it's a constant. If you multiply that by this constant, you multiply average by this as well. So we take out this. Now you take an average, you get average of x minus, well, average of x is just a number. So you have this average of x as well, times average of 1, vector 1. What is the average of vector 1? Is 1, right? All the elements are 1, no matter what's the length dimension of that. 10,000, 10,001, add them up, divided by 10,000, you still get 1. So you get 1, and you get, you don't need to write 1 because the number 1 is 0. The same thing is for the standard deviation. You just go ahead and take a standard deviation from both sides, or variance. You see that it's actually a unit variance or unit standard deviation. Okay, so Zscore will change, let's say, for the features. We have very different features. It changed all the features to zero mean and unit variance. It actually best works if the feature follows a normal distribution, but it still is used a lot in machine learning if the features do not follow some certain distribution. Okay, a normal distribution actually. Now, let's talk about the Cauchy-Schartz inequality. This is perhaps one of the most well-known inequality in many domains. Actually, that's used a lot in optimization and geometry as well, and vector calculus. Let's take a look at some of the application of that. So we define the inner product. Another definition of the inner product is as follows. This is not intended to use this one. What happened? This one, yes. A transpose B, dot product of A and B, is defined as norm of A times norm of B times cosine of theta. Okay, good. So in a sense, cosine of theta is equal to A transpose B divided by norm of A and norm of B. Let's use this one as equation 11. Okay, good. Now, cosine of theta, the range of cosine of theta is between -1 and 1. Okay, therefore, absolute value of the cosine of theta is less than 1, right? That's what it means that it's between -1 and 1. This means that absolute value of this quantity, equation 11, is less than 1, right? In a sense, this equation 12, if you write that, it's going to be, see, these norms are positive. Remember, norm is positive, one of the properties of norm. So you don't have to put the absolute value. So in a sense, this 12 is going to get converted to this one. It's less than 1 and greater than -1, of course, because it's actually greater than 0. Okay, so what we care about that is this one. If you multiply this together, multiply both sides by absolute, by norm of A and norm of B, you get this. Okay, so A transpose B, the absolute value of that, because dot product doesn't have to be positive, right, is less than or equal to norm of A times norm of B. This is known as a Cauchy-Schartz inequality, right? Cauchy-Schartz. If you expand that, also you get something interesting. So A transpose B is just a linear combination. It's just a linear function. A1, B1 plus A2, B2 all the way to A and Bn is less than or equal to, this is a definition of norm, and it's a definition of the norm of A and norm of B. Okay, good, great. So this is a Cauchy-Schartz. Now let's see one proof of triangular inequality. See, this is the third time we are looking at the triangular inequality in terms of Cauchy-Schartz now. So let's see. Let's use the color, the same color. norm of a plus b square. Remember the triangular inequality, norm of x plus y square, norm of x plus y is less than norm of x plus norm of y. So now let's square that, square the left hand side. Norm of a plus b square is equal to norm of a square. What is that? Let's see how we can calculate this. It's important to know how to manipulate the norm operation. This is calculated as follows, which is going to be A transpose A plus A transpose B plus B transpose A plus B transpose B. And that's what I have here, because we said that A transpose B and B transpose A are the same. Okay, good. Now we have this. Now let's use a Cauchy-Schartz inequality here. And let's use the relationship that we have in equation 11, right? We know that A transpose B, right, is, let me actually name this equation 13. This is the actual Cauchy-Schartz. Let me use this color. Okay, so let's go back here. Now we know A transpose B, as we see in equation 13, is less than or equal to this. Therefore, this term, this quantity, is smaller than or equal to this one, right? Okay, but what is this? What is this one? This is nothing but norm of A plus norm of B squared. Okay, so norm of A plus B squared is less than or equal to norm of A plus norm of B squared. Take a square root from both sides, you get this one. This is another proof for a triangular inequality based on Cauchy-Schartz. Okay, good. Now that we look at the triangular inequality proof in terms of Cauchy-Schartz, let's go back to this idea of an angle. This cosine of theta is equal to A transpose B over norm of A and norm of B. If you want to find the theta, all you do is just take a cosine inverse or arc cosine. So theta is equal to arc cosine of A transpose B divided by norm of A times norm of B. Okay, let's look at this. Let's evaluate this expression a little bit. If A transpose B is equal to 0, this is used a lot in literature. They say that vectors are orthogonal to each other when the dot product is 0. Now we will see why. If the dot product is 0, this term, this is 0, right? What is the angle that this cosine is 0? Now I did agree, right? I agree. So then A and B are orthogonal to each other. Great. What if the A and B are aligned to each other? What if this is for a case that A and B are like this? This is A, this is B. What if A and B are like this? This is A, this is B. What if A and B are aligned to each other, parallel to each other? Then the angle between them is 0. This is the angle. This theta is the angle between A and B. Then this is the angle between A and B is 0. Therefore, A transpose B is equal to norm of A times norm of B. And this is the time that equality happens. Otherwise, A transpose B is less than norm of A times norm of B. So when the angle between them is 0, then A transpose B is going to be maximum, right? Is equal to norm of A times norm of B. Why? Because cosine of theta is maximum. Great. A and B are completely aligned. Okay. In this case, it's good to note that is maximum. Good. So now let's continue. I have this alignment as well, but they don't have to have the same norm. Now, what if the theta is pi or 180 degree? This means that A and B have exactly opposite direction. In that case, A transpose B is equal to negative norm of A times norm of B. In that case, A transpose B is the minimum, right? The minimum value of A transpose B is negative norm of A times norm of B. So they are in exactly opposite direction, right? Good. Now, what if A theta is between 0 to pi over 2? Now, we don't get the exact value for the cosine of theta, but some important observation. Cosine of theta is greater than 0. So what are we talking about? We are talking about this one, right? If theta is somewhere here, in the first quadrant, the cosine of theta, look at the x-axis, cosine of theta, is positive. Therefore, A transpose B is positive. Therefore, the dot product between these two vectors are positive, right? Now, if theta is greater than pi over 2, when I say theta is greater than pi over 2, we mean theta is between pi over 2 and pi, right? So here, I guess it would be better to draw another circle for that. So this is for this case, and this is for this case. Then if theta is greater than pi over 2, cosine of theta is negative, which means that A transpose B is less than 0. Okay? So that's the evaluation of the angle for A transpose B, the dot product of the two vectors in terms of the norm as well. Okay, great. So now here I have some remark here. We talk about this, about the norm of sum of two vector. Drive this multiple times. What happens if you want to find the norm of x plus y? Easily, right? X plus y square, norm of x plus y square, x plus y transpose and x plus y, and you get x transpose x. You have done this yourself before. Okay. Now this x transpose y, you can write it based on angle, right? Because we know that what is x transpose y. We know x transpose y is in general become this cosine of theta. So that's what I've done. Okay. So it's worth noting that this equation perhaps can be equation 14. Okay. Now here we look at that if theta is equal to 90 degrees. Let's evaluate this equation 4D. If theta is 90 degrees, cosine of theta is 0, right? Then you get x plus y square, x plus norm of x plus y square is equal to norm of x square plus norm of y square. This is a famous theorem, Pythagoras theorem, right? Very, very important theorem, this one. In that case, this is this side, this is this side, this is this side. Anyway, right? So x norm of x plus y square is equal to norm of x square plus norm of y square. Okay. Now, what if theta is 0? What do we get? If theta is 0, then we get something very interesting. Cosine of theta is 1. So we get norm of x plus y square here is equal to this. But this is nothing but this. Norm of x plus norm of y square, this one. Take a square root from both sides. You get norm of x plus y is equal to norm of x plus norm of y. Wait a minute. Norm of x plus y is always smaller equal to norm of x plus norm of y. That's the triangular inequality. But now we get equality here. So equality for the triangular inequality happens when two vectors are completely aligned, when the angle between them is 0. I wrote it down here. Therefore, if x and y are aligned, the norm of that sum is equal to sum of their norm, which means equality for triangle inequality. Okay. So we talked about all these concepts. Now let's use another concept and relate them to all the concepts that we have learned before. Correlation coefficient. Here, when we talk about correlation, we are talking about the Pearson correlation. There are Kendall type of correlation, and there are some other nonlinear correlation as well. This is a Pearson, the one that is used widely in statistics. The correlation that you have heard mostly is the Pearson correlation, which is a measure of linear, remember linear, measure of linear correlation between two vectors, A and B, right? So correlation is coefficient, rho is defined as covariance of AB, defined by a standard deviation of A and a standard deviation of B, right? So this is the definition in terms of random variables. We look at in the third video. But I want to map it to this definition here, right? So A minus mu A, we all know, we are expert in this stuff. I write it AI, each component minus average of A, right? You don't need this one if you're writing it component wise, right? If you're writing component, the one is only needed when you're subtracting a constant from a vector. So AI minus average of A times BI minus average of B, sum them because of expected value outside this one, this expected value, and divided by n. Remember the PMF? Remember the average for the vectors? We have always 1 over n here. Okay, good. But in the third video, I will make sure that I put a link in the description. In the third video, we talk about this. What is this? I define this one, AI minus this as a bar, and this one as a B bar. So this is nothing but A bar transpose times B bar, right? This is dot product. What was the dot product of A and B? Nothing but AI BI. Isn't that the same thing? I'm doing exactly the same thing here. It's not, this is very important. I'm going to call it equation 15. Right? Good. But what is a standard deviation? This is stuff you know it very well. This is the definition of standard deviation of A, standard deviation of B, and now let's divide them together. We had this in video 3, but what we didn't have in video 3 is what we have right now here. Up to now we had it, we cancel out the 1 over n, but now wait a minute, what is this? Isn't that the definition of cosine of theta? We just defined the definition of cosine of theta. We defined cosine of theta somewhere. I'm gonna show it to you. Cosine of theta. Isn't this definition of cosine of theta equation 11? This is exactly the same here. So the Pearson correlation is equal to cosine of theta. And that's why Pearson correlation also is bounded between -1 and 1. The maximum happens when? The maximum happens when the theta is equal to 0. And when theta is equal to 90 degrees, two signals have no linear correlation. Remember, linear correlation with each other. Okay? So Pearson correlation also is bounded between -1 and 1, similar to cosine. Okay? So rho equal to plus minus 1 is perfect correlation. Rho is equal to -1 is a still perfect correlation, but in opposite direction. Right? And rho equal to 0 means absolutely no correlation, no trend between two vector or orthogonality. Okay, good. We map them, we define the correlation, we map it to the cosine of the angle, we define them based on the covariance, we define it based on the dot product. All is going great. But now let's talk about the concept that a standard deviation of the sum. You have a sum of two random variables or sum of two vectors. How can I define the standard deviation? Okay, a standard deviation of A plus B is equal to a square root of variance of A plus B, and variance of A plus B is defined as follows. This is a covariance, right? Okay, now we're going to talk about why this is correct. You have seen it before, but I'm going to first pause here a little bit to go over this equation with each other. So this variance of A plus B, if you want to see this one better, you can write it like this: expected value of A plus B minus mu of A, mu of B square. Okay, so let's write a little bit more. A minus mu of A plus B minus mu of B, okay, square. So it's gonna be expected value of A minus mu of A square, expected value of B minus mu of B square, plus 2 times expected value of A minus mu of A, B minus mu of B. Right, now it's clear, right? So this one is gonna be the variance of A This one is going to be variance of B. This one is going to be 2 covariance of A and B, right? So that's why we came up with this stuff. But now, so let's wait a minute here. Now let's go to the correlation we have. Isn't this a definition of the Pearson correlation? One of the definitions we have. Rho is equal to covariance of AB divided by a standard deviation of A times the standard deviation of B. So covariance of AB is equal to rho times a standard deviation of A times the standard deviation of B. Okay. So this is gonna, let's call this one equation 16 perhaps. Great. So a standard deviation of A plus B, in a sense, is equal to a standard deviation of A squared, which is just variance of A here. A standard deviation of B squared, which is just a variance of B. 2 covariance of A and B. But what is 2 covariance of A and B? It's 2 rho, a standard deviation of A, a standard deviation of B. So we call it equation 17. Seems that. Okay, so now we go. Okay, so that's equation 17. So there is a method 2 as well for people that don't want to use this probabilistic idea. Just follow the vector domain. A standard deviation of A plus B, as we are all expert in definition of standard deviation for vectors, is equal to 1 over the square root of n. N is the length of vector A plus B minus average of A plus B times the one vector. Good. So let's do this one. Average of A plus B, we all have seen that it's equal to average of A plus average of B, right? Okay. So I'm going to put the average of A times one vector here, average of B times B vector here. Okay, great. So now I'm going to call this one, see, we let this one A minus average of A to be A bar. We have done this trick before. And B minus average of B to be B bar. This is just to reduce the complexity. Otherwise, the equation is very messy. So this is what we have. This is what we are trying to compute, right? Let's call this one equation 18 here. This is what we are trying to compute. But we know how to compute the norm based on transpose, right? So what do we do here? What do we do? A plus B transpose A plus B bar, right? So you get A bar transpose times A bar. This is norm of A bar square, norm of B bar, should be B bar, times this. 2A transpose, no, 2A bar transpose times B bar. Good. Now I said according to the last part, yes. According to the last part, we are going to write this one as follows. Remember this definition of Pearson correlation that we related to the dot product and standard deviation, right? Or the norms. I drive it here. This one. I said according to last part, I mean here. So then rho, so A bar transpose times B bar is equal to rho times norm of A bar times norm of B bar. Okay, good. All I'm going to do is just replace it here. That's what according to last part means, right? Okay, great. So now if you do this one, what would you get? You get, remember this A bar, what was this A bar, right? We want to write it based on the A and B. This, I'm gonna go ahead and copy this here. Okay. You see, norm of isn't that the A bar, normal A bar? This is just A bar, a square, right? Great. What you can do, you can just bring this 1 over n inside, and you will see that this is like this. You can take this 1 over n inside this, because 1 over n. So this becomes what? A standard deviation of A squared. right? Plus a standard deviation of the B score, plus this A and B, you write it based on 2 row, a standard deviation of A times the standard deviation of B. Remember this one, right? Remember? Let me just write a little bit further here. This is this one. Let's write it here. This A bar, norm of A bar, is equal to norm of A minus B minus average of B. Right? Remember, this is just equal to this. Remember, it's very similar to the covariance, right? So it's equal to 2 rho times the standard variation of A times a standard deviation of the B. Okay, good, great. So that's it about the standard deviation of the sum. Then you can condition on what happened to the row. If row is 0, what do we get? If row is 0, we get the standard deviation of A square plus standard deviation of B square. If the row is equal to 1, right, then you can argue about these terms actually, right? So remember, when you bring this 1 over n inside this, you square that, you bring this inside. Let me right, and then that's why you get the standard deviation of A square. So you can don't need to this one, there is no need. But here, for example, you take this a square root of n inside, so it becomes 1 over n once it goes inside the a square root. Okay, great. So the final expression is going to be this one, and the way to drive that, we all know how to drive it, right? So and in terms of the condition based on row, you sometimes say row is 0. Well, let's see what happens. Row is -1, and let's see when row is +1. Okay, good. Let's talk about complexity and flops. I talked about that in the first video. I said that in the future videos I'm going to talk about that more. So number of flops for norm of a vector. What is that? Let's see. What is the operation that we need? Each square root is 1 flop, but forget about that for now. x1 x squared is x1 by times x1. This is 1 flop. x2 times x2 is another flop. So how many we have? We have n flops here. How many addition we have? N minus 1. So we have n square, we say n square plus n minus 1 addition plus 1 square root. You get what? 2n minus 1. You get 2n minus, you get 2n. Right? You get 2n. What's going to be the complexity? We said constant never matters. It's going to be O of n. O of n. So this is this. But 2n flops. And O of n is the one that matters for us. Let's move on. Number of flops for RMS of x. What is the number of flops for RMS? Let's forget what the square root of n in the denominator, because we want to find the approximate value. What is the number of flops for the norm? It's just 2n. And let's forget about this divided. Divided is division is 1 flop and a square root of n another one. So you get 2n plus 2 flops. But we don't care about that. What we care about is that it's going to be, let's say it's going to be 2n plus 2 flops, which is going to be order of n again. Let's talk about the distance of A and B. We define to be norm of A minus B, or norm of A minus B. Okay, good. Let's write a couple of terms. A1 minus B1 square plus A2 minus B2 square all the way to AN minus BN square. Right. So here I said how many square we have. First of all, what do? We are subtracting. How many subtraction we have? How many subtraction we have? 1, 2, how many? N. So let's just do this one again from scratch. N subtraction. I want to show you how to calculate that. Right. Then what do? We raise it to the square. How many? N Then how many addition you have? N minus 1. So you get 2n, 3n minus 1. And then you have a square root as well. So you get 3n. So right, so you get 3 envelopes. But it's going to be in the order of n, right? Again, on. STD of A, a standard deviation of A. Let's see what is that. To calculate the average, how many envelopes do we have? Let's take a look at that to calculate the average. A1 plus A2 all the way to n divided by n. Right. So here we have in the order of, let's say, envelopes. N minus 1 addition divided by n 1 is become envelopes. You multiply this one by vector 1, you get another envelopes here. So you have 2 envelopes here, right? So, or you can just say that when you multiply the average of A by 1, you can just get 1 envelopes here. Depends on how you can actually calculate. That's why the order only matters. A minus this, subtraction, right? This is a vector subtraction, right? Remember, it's a vector subtraction. It's like this. A minus average of A1. A2 minus average of A. N minus average of A. Okay, so you have n subtraction here as well. That's why I wrote the n here. Now we don't care about the 1 over the square root of n as well. And then for this norm, you get 2 envelopes, right? So you get 2 envelopes here plus envelopes, 3n plus 1 envelope you had here, you get in the order of 4n. Sometimes you calculate differently, you get 5 envelopes. What matters to us is that in the order of big O of n. So order of envelopes, the constant doesn't matter. 7n, 4n, 3n, we don't care about that, right? Because this is, after all, it's a rough estimate, right? So you can say the average of A times 1, if average of A is pre-computed, is a constant, times 1, we get envelopes here, right? This is envelopes, that's what, right? You get envelopes here, this is the whole thing. A minus that, that's what I said, that we get another envelope here, 2 envelope, and the norm of A, because you square that, and then you calculate this summation, you get 4 envelopes. 2n for the norm we had, and then 2n before we get 4 envelopes. Okay, correlation coefficient. Correlation coefficient. So we see that for the norm, we get 2 envelope, we get 4n. For this A bar transpose times B bar, right? So what was this A bar? Right. So what is this A transpose B? How many operations we have for A transpose B? Did I calculate this one? No. So it's good. Actually, I calculated the first video, I guess. So it requires n multiplication and n minus 1 addition. So you get 2n minus 1 in the order of 2n. Let's say 2n, right? And then you get 1, 2n, 1, 2n here. But for this operation, n minus average of A. So we get envelope here to calculate this one, and n minus A minus this also is another n. So this one we have 2 envelopes here, and for B bar also you have 2 envelopes. For this one, let's not write 2n minus 1, let's say 2 envelopes, and then 2n and 2n here as well. So you have 5 times 2n, so you get in the order of 10 envelopes, which is again O of order n. Okay, so that's how you calculate the number of envelopes. The video got a little long, but this is all I wanted to talk about that as far as the correlation, norm, standard deviation, variance, inequalities, triangle, Cauchy-Schartz, and many more that we discussed in this video. Thank you so much for listening. See you all in the next video. Thank you.